Fun fact, did you know that indoor air can be more polluted than outdoor air? It seems counterintuitive, doesn't it? But especially when you're talking about large groups of people like schools, for instance. Educational facilities can have indoor air pollutants that are up to 5 times higher than outdoor air. And it's not just carbon dioxide, it's cleaning chemicals, it's dust, it's off-gassing from paints and stains and carpets and furniture and a whole host of items. And here's another fun fact. Approximately 56 million people, that's 20% of the population, spend their days in elementary and secondary schools. That's a lot of people. Now, studies have shown that proper ventilation in schools helps reduce the risk of respiratory infections and allergies, minimizes carbon dioxide levels, and improves cognitive function in students. Unfortunately, schools are continually challenged by the need to provide this fresh, clean outdoor air to dilute CO2 as well as other indoor air contaminants, but at the same time applying the necessary resources and technology to tame the cost of treating this outdoor air for comfort. So current code compliance means that an average classroom in the United States with 25 students is going to require approximately 375 CFM of outdoor air. And that's regardless of outdoor temperature. So whether it's negative 25 degrees Fahrenheit or 105 degrees Fahrenheit, you're going to need 375 CFM for that sample classroom. On a 95-degree day, which is typical here in Florida, that could mean an additional 18,000 BTUs just to treat that outdoor air coming in for ventilation. So understand while the final amount may be minimized by sensing controls or other means, a large part, if not the largest part of a school's operating budget is concerned with HVAC and the cost of tempering or conditioning that outdoor air coming in for ventilation. And that's why we strongly encourage the use of energy recovery ventilators in all school projects that utilize barred manufacturing indoor or outdoor HVAC products. The BARD series of energy recovery ventilators are an extremely simple ventilation option that allow the schools to recover part of the sensible and latent characteristics of the indoor air while it's being exhausted and to transfer those characteristics to the raw outdoor air as it's drawn into the building. While it sounds complicated, it's not. There are very few moving parts to this idea. Essentially, at the core of the machine, the energy recovery ventilator is a series of 2 wheels made of a wound polymer filament with a desiccant coating. The wheels simply spin between the exhaust air channel and the raw outdoor air channel. During half of a single revolution, 50% of the wheel is in the exhaust. And there it captures the sensible temperature of the return air and also releases some latent moisture into that same air as it leaves the building. The opposite side of the wheel is in the raw outdoor air intake. Now it's tempering incoming temperatures and absorbing moisture. As the wheel spins, it repeats this cycle over and over and over again, multiple times per minute. In this example, the resulting exchange can mean almost 70% of the energy is recovered, nearly 12,000 BTUs for one classroom. The energy recovered lowers the amount of cooling required, possibly reducing the size of the equipment necessary, and also reduces operating expenses for the HVAC equipment. So now we understand why we need an ERV, and additionally how an ERV works internally. Let's take a look at some of the moving parts. Besides the rotating ERV wheels, there is typically a pair of dual shaft blower motors, one on the intake and one on the exhaust, along with speed taps to adjust speed and pressurization. Additionally, there's going to be 1 or 2 drive motors to rotate those ERV wheels, along with belts and pulleys. Control-wise, there's typically going to be a single ventilation relay waiting for a 24-volt signal from the A terminal, which is going to energize the whole system with high voltage, initiating the blower and the drive motors. So troubleshooting becomes a simplistic tree. Do we have a call for ventilation? Is the relay functional? And by that, is it getting 24 volts and is it closing the contacts to allow the high voltage circuit to energize? Are the blower motors functional? Are the blower wheels tight? Do the drive motors engage, rotating the pulleys, and are the belts intact that drive the ERV wheels? It's a simple step-by-step approach to solve any ERV problem. Routine maintenance on ERVs should be completed at least every 6 months and consists of minimal clean and check functions. Access to the ERV is easily done through the front ventilation panel on smaller wall mounts, and through either side for larger wall mounts. Number 1, check the air intake filter. Clean if necessary. Number 2, check the system air filters. Replace if necessary. Number 3, check for proper rotation. Energize the ERV to check the drive motors, the belts, and the pulleys. Any chirps or squeaks can be eliminated by lubricating the belt and pulleys with LPS1 dry film lubricant only. This is not an oil, it does not break down the belt, it does not attract dust or dirt. LPS1 is the only lubricant you should be using. Blower motor, the drive motor, and the wheel bearings are all permanently lubricated. They do not need any additional lubrication. Number 4, check for debris on both sides of the wheels. Disconnect the unit from high voltage and clean using a soft bristle brush and a shop vac. Gently agitate and loosen debris from the polymer filaments. Using the shop vac, in reverse, gently blow the remaining debris from the wheels. If the wheels exhibit staining or the need for a more thorough cleaning, the polymer filaments may be washed with a dilute dish detergent or Formula 409. Wheels may not be immersed in liquid, but they can easily be removed from the cassette tray for better access. Follow the exploded diagram in the IOM for a detailed look at this process. Having a properly maintained and operating ERV is one thing, but how to control that ERV, that's something else altogether. Yes, an ERV is saving you money whenever it's running, but the real question is, how often should it be running? Old school thinking revolves around scheduling that ventilation to be continuous during occupied periods of the day, the school day. So let's say between 7 a.m. and 4 p.m. But that can be wasteful, especially when you consider teacher planning periods, or teacher work days, or holidays, or other times when occupancy is low. You certainly don't need 375 CFM of ventilation at those times. Modern, progressive control strategies like to use carbon dioxide as a marker for indoor conditions. With a CO2 sensor in the classroom, ventilation occurs as carbon dioxide crosses a threshold and not before. And then it reduces ventilation or stops it altogether as carbon dioxide levels recede. If you're not sure what strategy or controls are best for your situation, do not hesitate to contact your AccuAir representative. After all, AccuAir has the answers.